Look up tonight, and you'll see it. A luminous sphere hanging in the darkness, so familiar that we rarely stop to question its presence. But what if I told you that without this celestial companion you wouldn't exist? That the moon isn't just a beautiful ornament in our night sky, but the silent guardian that made complex life on Earth possible? For the next hour, let's journey together across 4.5 billion years of history, from a violent cosmic collision to humanity's return to the lunar surface. Come with me. Let's discover why this ancient world, forever showing us the same face, holds the secrets to our very existence. Our story begins 4.51 billion years ago, in an infant solar system still forming from clouds of gas and dust. The young Earth had just taken shape, barely 60 million years old, orbiting a newly ignited sun. But Earth wasn't alone in its orbital path. Another world, roughly the size of Mars, traced a similar trajectory around our star. Scientists call this vanished planet Theia, named after the Greek Titaness who gave birth to the moon goddess. For perhaps millions of years, these two rocky worlds danced closer and closer, their gravitational fields gradually pulling them into an inevitable cosmic catastrophe. Neither world would survive what came next. Imagine standing on the early Earth's surface, though you wouldn't survive even a moment in this hellish environment. The atmosphere is toxic, the surface is partially molten, and volcanic eruptions constantly reshape the landscape. Then, on the horizon, a sight that defies comprehension, a planet grows larger in the sky. Theia approaches at over 33,000 kilometers per hour, 9.3 kilometers every second. This isn't a head-on collision, but a glancing blow at a 45-degree angle. In the final seconds, Theia fills half the sky. Then comes impact. The energy released equals billions of nuclear weapons detonating simultaneously. The universe changed forever in that moment. The impact is beyond description. Theia's outer layers instantly vaporize into a superheated plasma cloud reaching temperatures of 7,000 degrees Celsius. The shockwave travels through both planets at hypersonic speeds, liquefying rock kilometers below the surface. Theia's iron-rich core punches through the planet's mantle and plunges toward Earth's core, where the two metallic hearts merge into one. Meanwhile, an unimaginable amount of material, mostly from both planets' mantles, explodes outward into space. Rock, vapor, and magma spray out in a vast cloud, some particles reaching escape velocity while others fall back to the devastated surface. In mere hours, not years or months, this debris begins to coalesce into a new world. From this ring of destruction, our moon is born. Recent computer simulations reveal something extraordinary. The moon formed in hours, not the months or years scientists previously believed. Ejected material immediately begins clumping together through gravity, with the nearest particles accreting fastest. Within a single Earth day, a molten sphere takes shape in orbit, measuring about 3,474 kilometers in diameter, roughly 1/4 Earth size. This new world orbits incredibly close, perhaps only 22,500 kilometers away, compared to today's 384,400 kilometers. From Earth's devastated surface, if anything could observe it, the infant moon would appear 15 times larger than the moon we see today, dominating the sky with its angry red glow. The infant moon is entirely molten, a global magma ocean between 200 and 1,000 kilometers deep, with surface temperatures reaching 1727 degrees Celsius. You're witnessing the lunar magma ocean period, and it will persist far longer than scientists initially thought. For over 200 million years, this world remains in a semi-molten state, slowly cooling in the vacuum of space. There's no atmosphere to radiate heat away efficiently, so the cooling happens gradually, over geological epochs. During this time, minerals begin to crystallize in a process called magmatic differentiation. Denser materials sink while lighter materials float, and through this simple physical process, the moon develops its layered structure, core, mantle, and crust. Slowly, over millions of years, the moon's internal structure emerges. First, heavy minerals like olivine and pyroxene crystallize and sink, forming the mantle. Then, a remarkable process occurs at the top of the magma ocean. Crystals of plagioclase feldspar, being less dense than the surrounding melt, begin to float upward like cream rising in milk. These crystals accumulate at the surface, gradually forming a bright, aluminum-rich crust we call anorthosite. Between these layers, the last 1% of crystallization traps unusual elements: potassium, rare earth elements, and phosphorus, collectively known as keep. This primordial lunar crust, formed 443 billion years ago, still exists today, preserved on the moon's Highlands, a monument to the solar system's violent youth. The moon that emerges from this fiery birth is profoundly different from Earth. Its core is tiny, only 330 kilometers in radius, containing just 20% of the moon's diameter compared to Earth's core, which is 50%. Ooh. During the giant impact, most of Thea's iron core merged with Earth's, leaving the newly formed moon with relatively little heavy metal. This small core would have profound consequences for the moon's evolution. Without a large, churning metallic core, the moon could never generate a strong magnetic field. Without a magnetic field, solar wind would constantly bombard its surface. The moon would remain geologically simpler, its interior cooling faster than Earth's, eventually becoming the quiet, airless world we see today. Recent discoveries add fascinating complexity to this formation story. In December 2024, scientists proposed that some lunar rocks previously dated to the moon's formation actually record a later event. Tidal heating from the nearby Earth caused remelting billions of years after the initial formation. The moon, orbiting so close to our planet, experienced immense tidal forces that kneaded its interior like dough, generating heat through friction. This revelation reminds us that scientific understanding constantly evolves. What we know today about the moon's birth represents our best current understanding, built on decades of sample analysis, computer simulations, and theoretical physics. Yet mysteries remain, waiting for future missions to unlock them. The moon's formation story is still being written. Gaze at the full moon tonight, and you'll see its face painted in light and shadow-bright regions and dark patches, creating the patterns humans have interpreted as faces, rabbits, or landscapes for millennia. These aren't illusions or tricks of light. They're real geological features, each telling a chapter in the moon's 4.5 billion year story. The bright areas are ancient highlands, the moon's primordial crust formed when plagioclase crystals floated to the top of the magma ocean. The dark regions are Maria, Latin for seas, vast plains of volcanic rock that flooded into giant impact, basins billions of years ago. This dichotomy of dark and light isn't just beautiful. It reveals the moon's violent history and continuing geological evolution. Let's descend toward Mare Tranquillitatis, the Sea of Tranquility, where humanity first set foot on another world on July 20, 1969. From orbit, this vast dark plain appears smooth. But as we approach, subtle textures emerge, gentle wrinkle ridges where ancient lava flows compressed, scattered impact, craters of all sizes, and rays of bright ejecta from distant impacts. The basalts here crystallized 3.5 billion years ago from lava that oozed up through cracks in the lunar crust. These weren't explosive eruptions like Earth's volcanoes, but rather effusive flows where low-viscosity magma spread across vast distances, accumulating in layers 10 to 20 meters thick. Over millions of years, repeated eruptions built up deposits 500 to 500 meters deep, Mare Imbrium. The Sea of Rains tells an even more dramatic story. This massive circular basin, 1,145 kilometers in diameter, formed 3.85 billion years ago when an asteroid perhaps 250 kilometers across struck the Moon with apocalyptic force. The impact was so powerful it created concentric rings of mountains. The visible remnants are the Montes Alps, Apennines, and Caucasus that circle the basin today. For hundreds of millions of years after the impact, the basin remained a depression in the lunar crust. Then, between 3.1 and 3.3 billion years ago, basaltic lava began flooding the interior, flowing through fractures opened by the ancient impact. The result is the largest continuous mare on the near side, visible to the naked eye as the right eye of the man in the moon. But here's something that changed everything we thought we knew about the Moon. In December 2020, China's Chang'e 5 spacecraft returned samples from Oceanus Procellarum. Scientists expected ancient basalts similar to Apollo samples. Instead, radiometric dating revealed these rocks crystallized just 203 billion years ago. Let's let that sink in. Volcanic eruptions on the Moon, flooding the surface with fresh lava, occurred 800 to 900 million years beyond when scientists believed volcanism had ceased. Even more astonishing, volcanic glass beads in those samples dated to just 123 million years ago, meaning lava reached the lunar surface while dinosaurs roamed Earth. The supposedly dead Moon was alive far more recently than we ever imagined. Now, let's journey to the ancient highlands that cover most of the lunar surface. These bright, heavily cratered terrains date to 4.0 to 4.5 billion years ago, nearly as old as the Moon itself. Every square meter bears the scars of impacts, craters overlapping, craters in a palimpsest of destruction written over billions of years. The rock here is an orthosite containing over 90% plagioclase feldspar, the crystals that floated to the top of the magma ocean. This is the Moon's primordial crust, the original surface that solidified as the newborn world cooled. Stand on these highlands, and you're standing on material older than any rock on Earth's surface, a direct connection to the solar system's violent infancy. The Maria cover about 31% of the near side we see from Earth, but here's a profound mystery. They cover only 1% of the far side. Why this dramatic asymmetry? The answer lies beneath the surface. The near side crust averages 25 to 40 kilometers thick, while the far side crust reaches 60 to 100 kilometers deep. Magma rising from the Moon's interior could more easily break through the thinner near side crust, flooding the giant impact basins there with lava. The far side's thicker crust formed a more effective barrier, preventing most volcanic eruptions. This fundamental asymmetry means the two hemispheres of the Moon had dramatically different geological histories, essentially evolving as different worlds despite being part of the same body. NASA's Grail mission, which orbited the Moon from 2012 to 2024, revolutionized our understanding of what lies beneath the surface. By measuring tiny variations in the Moon's gravity with unprecedented precision, Grail revealed that the lunar crust is thinner than previously thought, 34 to 43 kilometers on average, not the 50 to 60 kilometers earlier estimates suggested. More surprisingly, the crust is fractured and porous throughout, with about 12% of its volume consisting of empty space. Billions of years of meteorite bombardment have pulverized the outer layers of the moon to great depths, shattering the rock into a complex network of cracks and voids. The moon's crust isn't a solid shell, but a fractured, fragmented layer, a testament to 4.5 billion years of cosmic violence. Impact craters are the moon's most defining feature, covering every square meter of its surface in a dense tapestry of overlapping circles. From microscopic pits smaller than a grain of sand to vast basins the size of countries, these features record 4.5 billion years of cosmic bombardment. Unlike Earth, where wind, water, and tectonic activity constantly erase the evidence of impacts, the moon preserves every scar. No atmosphere exists to burn up incoming meteorites. No rain falls to erode crater walls. No tectonic plates shift to recycle the crust. On the moon, once an impact occurs, its record remains nearly forever, a pristine geological library waiting to tell us about the history of bombardment throughout the inner solar system. Let's witness an impact. A meteorite perhaps 10 meters across hurtles toward the moon at 17 kilometers per second, 40 times faster than a bullet. At these velocities, the kinetic energy is immense, equivalent to thousands of tons of TNT. The meteorite doesn't simply punch a hole in the surface. Instead, in the fraction of a second of contact, the shock of impact converts kinetic energy into heat so intense that both the projectile and target rock instantly vaporize. A supersonic shockwave races outward through the bedrock, pulverizing everything in its path. Rock behaves like fluid under these extreme forces, flowing and splashing outward. In just seconds, a crater forms many times larger than the original projectile, a bowl-shaped depression carved by pure energy. For large impacts, gravity reshapes the initial crater through a process called modification. The transient crater forms in seconds, a deep, bowl-shaped cavity. But this shape is unstable. The crater walls, too steep to support themselves in the moon's gravity, slump downward, forming terraced walls. Material from deep beneath the impact point, compressed by the shock wave, rebounds upward, creating central peaks that rise kilometers above the crater floor. These peaks expose rock from far below the surface, material that would otherwise remain forever hidden. To planetary geologists, crater central peaks are like windows into the moon's interior, samples of deep crust or even upper mantle brought to the surface by the violence of impact. Tycho crater exemplifies the beauty and violence of young impacts. This magnificent crater, 85 kilometers across and 4 kilometers deep, formed just 108 million years ago during Earth's Cretaceous period, making it remarkably young in lunar terms. From Earth, Tycho appears as the brightest spot on the full moon, a brilliant white bullseye surrounded by spectacular rays that extend up to 500 kilometers across the near side like splashes of white paint on a gray canvas. These rays are ejecta, rock pulverized by the impact and thrown hundreds of kilometers from the crater. The brilliant white color tells us this material is fresh, unweathered by space radiation, giving us a glimpse of what all lunar impacts look like when newly formed. Copernicus crater, larger and older than Tycho, formed 800 to 900 million years ago. At 93 kilometers in diameter and nearly 4 kilometers deep, Copernicus rivals the Grand Canyon in depth. Its central peaks rise a kilometer above the crater floor, appearing as a cluster of mountains when viewed from the surface. Stand on those peaks and look around. You can see the circular crater walls in all directions, defining your world's horizon. The sloping rampart descends 30 kilometers outward from the rim before blending into the surrounding terrain. Copernicus's ray system remains visible despite the crater's age, extending at least 800 kilometers. These rays overlay other features, demonstrating that Copernicus's relatively young impacts that occurred before Copernicus have their own rays buried beneath its ejecta. The South Pole. Aitken Basin represents impact violence on an almost unimaginable scale. This colossal scar measures 2,500 kilometers in diameter, roughly the distance from New York to Los Angeles, and plunges 13 kilometers below the surrounding terrain, making it the largest and deepest impact basin in the solar system. The impactor that created this basin was probably over 200 kilometers across, striking over 4.1 billion years ago during the late heavy bombardment period when asteroids and comets pelted the inner solar system. The impact excavated material from so deep it may have reached through the crust into the mantle itself. If this is true, then the rock exposed in this basin offers an unprecedented opportunity to sample the moon's interior without drilling. Every crater tells a story about when it formed through a remarkable natural process called crater counting. Older surfaces have more craters because they've been exposed to bombardment longer. Younger surfaces have fewer craters because less time has passed for impacts to accumulate. By carefully counting the number and size of craters in a region and comparing these statistics to areas of known age, planetary scientists can estimate when that surface formed, even without physical samples. This technique revealed that the Maria are younger than the Highlands, that different mare regions formed at different times, and that the bombardment rate wasn't constant but varied dramatically during the moon's early history. Each crater is a clock, and collectively, they tell the story of time itself. China's Chang'e 6 mission, which returns samples from the South Pole. Aitken Basin's interior in June 2024 may finally reveal whether this ancient impact truly excavated mantle material. The samples contain basalts dated to 228E7 billion years ago, but more importantly, their chemical composition differs from near-side samples, lower in the KREEP elements that characterize near-side material. Are we seeing mantle rock brought to the surface by the impact? Or just deep crustal material? These questions await detailed analysis. What we know is this. Understanding this impact helps us understand the moon itself. Imagine standing on the lunar surface, and everywhere you look, covering every rock, filling every crater, blanketing every feature, lies a layer of fine gray powder. This is lunar regolith, and it's unlike any soil on Earth. It wasn't formed by biological decay, chemical weathering, or water erosion. Instead, this material is the pulverized remains of 4.5 billion years of meteorite bombardment. Every impact, from continent-sized asteroids to microscopic dust grains, grinding the surface into progressively finer particles. On young Maria surfaces, the regolith layer is 2 to 3 meters thick. On the ancient Highlands, it reaches 20 meters deep. It's the moon's skin, its outer layer, and it holds secrets about the entire history of the solar system. The Apollo astronauts described regolith as having a distinctive quality. It smelled like spent gunpowder and had a peculiar taste. The material is charcoal gray, sometimes with brownish or reddish tints depending on the local rock composition. When you disturb it, it behaves strangely. Cohesive, clinging together more than dry sand would, yet it flows freely once disturbed. The particles are angular and sharp, freshly fractured surfaces with no erosion to round their edges. These sharp fragments abraded the astronauts' spacesuits, worked their way into equipment seals, and proved surprisingly difficult to manage. The moon's most abundant surface material became one of the most challenging aspects of working on the lunar surface. Regolith composition reveals the moon's chemical diversity. Maria regolith is rich in iron, magnesium, and titanium, giving it a darker color, sometimes nearly black in high titanium regions. Highland regolith contains abundant aluminum, calcium, and silicon, but little iron, creating its characteristic bright appearance. Within the regolith are four main components: rock fragments from the local bedrock, individual mineral grains liberated by impacts. Impact glass is formed when meteorite strikes instantly melt and rapidly cool rock, and most intriguingly, agglutinates, constructional particles unique to airless bodies. Agglutinates form when micrometeorite impacts weld together mineral fragments with a glassy matrix containing nanophase metallic iron. In mature soils, agglutinates comprise about 50% of the material by volume. The regolith is electrically charged, a phenomenon that caused unexpected problems during Apollo missions. Without an atmosphere, ultraviolet radiation from the sun liberates electrons from surface particles, giving them a positive charge. Near the terminator. The Apollo astronauts observed glows and streamers above the horizon after sunset, likely caused by sunlight scattering off these electrostatically levitated particles. This behavior means dust doesn't simply lie inert on the surface but can actively migrate, contaminating equipment and solar panels. Future missions must account for this dynamic behavior. 5 processes continuously modify the airless lunar surface in a phenomenon called space weathering. First, micrometeorite bombardment. A constant rain of particles from nanometers to meters serves as the primary erosion mechanism, pulverizing surface material at a rate of about 1 millimeter per million years. Second, solar wind bombardment strikes the surface directly with high-energy protons, sputtering atoms from mineral surfaces and implanting hydrogen, helium, carbon, and nitrogen. Third, cosmic rays penetrate several meters, breaking apart atomic nuclei. Fourth, unfiltered ultraviolet radiation breaks molecular bonds and charges the surface. Finally, thermal cycling creates stress fractures as temperatures swing 300 degrees Celsius between day and night. These processes work simultaneously, gradually changing the optical and physical properties of surface materials over time. Space weathering gradually darkens the surface over time, creating what planetary scientists call optical maturity. Fresh craters and their rays appear bright white because they expose unweathered material from below the surface. Over millions of years, as space weathering processes operate, this fresh material darkens and reddens, eventually matching the surrounding terrain. By measuring the optical properties of a surface, its brightness and color, scientists can estimate its exposure age independently of crater counting. The brightest, freshest features on the moon are just thousands to millions of years old. The darkest, most mature regolith has been exposed for billions of years, recording the entire history of space weathering in the inner solar system. The regolith is more than just dust. It's a chemical history book. Solar wind atoms implanted over billions of years preserve a record of the sun's composition and activity. Rare isotopes created by cosmic ray bombardment allow scientists to date how long rocks have been exposed on the surface. Glass spherules contain dissolved gases from ancient volcanic eruptions. Some particles even contain micrometeorite fragments from asteroids, providing samples of bodies we've never visited. Every handful of regolith contains material from multiple impacts mixed together, a complex blend representing the entire region's geological history. The moon may lack the biological richness of Earth's soil, but its regolith holds equally precious scientific treasures waiting to be decoded. Here's a remarkable fact that most people never question. The moon always shows us the same face. The familiar pattern of Maria and Highlands you see tonight is identical to what your ancestors saw 10,000 years ago, what dinosaurs saw 100 million years ago, what primitive life forms saw 3 billion years ago. Throughout Earth's entire history, from whatever location on our planet's surface, observers have seen the same lunar hemisphere. The moon rotates on its axis at exactly the same rate as it orbits Earth, one rotation every 27,32,1661 days, one orbit every 27,32,1661 days. This perfect synchronization isn't coincidence. It's the inevitable result of gravity and time, a phenomenon called tidal locking that affects all large moons throughout the solar system. But the moon hasn't always been locked this way. When it first formed 4.51 billion years ago, orbiting perhaps just 22,500 kilometers from Earth, 15 times closer than today, the moon spun much faster, completing a rotation in perhaps just 8 hours. From Earth's surface, that newborn moon would have appeared 15 times larger than today, racing across the sky as its face changed hourly. How did this rapidly spinning world slow to its current synchronized state? The answer lies in tides, not ocean tides on the moon's surface, but tides in the moon's interior, solid rock distorted by Earth's powerful gravitational field. Let me show you how gravity can slow an entire world's rotation over hundreds of millions of years. Imagine the young moon as a ball of still warm rock orbiting close to Earth. Earth's gravity doesn't pull equally on all parts of the moon. It pulls hardest on the near side, less on the center, and least on the far side. This differential gravitational force stretches the moon into a slightly elongated football shape, with its long axis pointing toward Earth. Now, as the moon rotates, this tidal bulge tries to rotate too. But there's a problem. Rock has internal friction. It takes time for the bulge to rise and fall as different parts of the moon face Earth. The bulge lags slightly behind the moon's rotation, creating a misalignment. Earth's gravity pulls on this misaligned bulge, creating a torque that acts like a brake, gradually slowing the moon's rotation. Over hundreds of millions of years, this gravitational brake steadily slowed the moon's rotation. The rotational energy dissipated as heat in the moon's interior through friction and deformation. Gradually, inexorably, the rotation rate decreased. Eventually, the moon's rotation slowed until one complete spin took exactly as long as one orbit around Earth. At this point, the tidal bulge became permanently aligned with Earth. With the bulge no longer moving relative to Earth, no more energy needed to dissipate. The moon reached equilibrium, tidally locked. One hemisphere permanently facing Earth, the other permanently facing away. This process is so reliable that essentially all large moons in the solar system are tidally locked to their planets. It's not a rare phenomenon, but a natural consequence of orbital mechanics and time. The same tidal forces that locked the moon to Earth are now locking Earth to the moon. But this process is much slower because Earth is 81 times more massive. Currently, the moon raises tidal bulges in Earth's oceans, and Earth's rotation carries these bulges ahead of the moon. The moon's gravity pulling on these offset bulges gradually slows Earth's rotation while simultaneously pushing the moon into a higher orbit. In about 50 billion years. Far beyond the sun's lifetime, Earth would become tidally locked to the moon as well. At that point, one Earth day would equal one lunar month, both lasting about 47 of our current days. From one hemisphere of Earth, the moon would appear stationary in the sky, never rising or setting. From the other hemisphere, the moon would never be visible at all. Because the moon is tidally locked, we never see its far side from Earth. But that doesn't mean there's a dark side. This is one of the moon's most persistent misconceptions. The sun illuminates both sides equally over the course of a month. When we see a new moon, the far side is fully illuminated by the sun. When we see a full moon, the near side is lit while the far side is dark. Every location on the moon experiences approximately 14 days of continuous sunlight, followed by 14 days of continuous darkness as the moon orbits Earth. The term dark side historically meant unknown or unexplored, not permanently shadowed. The far side remained mysterious only because it was perpetually hidden from Earth-based observers until 1959, when Soviet spacecraft Lunar 3 photographed it for the first time. Though tidally locked, the moon doesn't show us exactly the same view all the time. A phenomenon called libration allows us to peek around the edges, eventually revealing about 59% of the lunar surface from Earth rather than just 50%. Libration in longitude occurs because the moon's orbit is elliptical. At closest approach, it moves faster than it rotates, revealing its eastern edge. At farthest distance, it moves slower, revealing its western edge. Libration in latitude happens because the moon's equator tilts relative to its orbital plane, allowing us to look over the north and south poles at different times. These gentle nodding and wobbling motions mean the moon's face isn't perfectly fixed, but shifts subtly over time, revealing a hidden strip of terrain around the edges. Throughout human history, the moon's changing face has marked time, inspired mythology, and guided agricultural cycles. But the phases aren't mysterious or magical. They're the natural result of geometry and light. The sun always illuminates exactly half of the moon, just as it illuminates half of Earth. What we see from Earth is simply which portion of that illuminated half happens to face us as the moon orbits our planet. The phases result from the constantly changing angle between the sun, moon, and Earth. Understanding this simple geometric relationship reveals not just the mechanics of lunar phases, but the fundamental nature of light and shadow throughout the solar system. Let's walk through the complete cycle together, from darkness to brilliance and back again. The cycle begins at new moon, when the moon passes between Earth and sun. From our perspective on Earth, we see only the moon's night side, the half facing away from the sun, so the moon appears invisible in the daytime sky. The moon rises and sets with the sun, lost in the solar glare. This alignment is usually imperfect. The moon's orbit tilts about 5 degrees relative to Earth's orbit around the sun, so the moon typically passes slightly above or below the sun. But occasionally, perhaps twice a year, the alignment is precise and the moon's shadow falls on Earth's surface. We call this a solar eclipse, one of nature's most spectacular displays, possible only because of the cosmic coincidence that the moon appears almost exactly the same size as the sun in our sky. Within a day or two of new moon, a magical sight appears in the western sky just after sunset, the waxing crescent. A delicate sliver of light curves against the darkening sky, a fingernail paring of the moon beginning its monthly journey toward fullness. The word waxing means growing, and each night the illuminated portion expands as the moon moves eastward in its orbit around Earth. Look carefully during this phase, and you might notice something extraordinary. The dark portion of the moon glows faintly, showing details of Maria and Highlands in a ghostly light. This phenomenon, called earthshine, occurs because sunlight reflects off Earth's clouds, oceans, and land, illuminating the moon's night side. From the moon's perspective, Earth appears nearly full, shining 40 times brighter than a full moon appears to us. As the moon continues its eastward journey, it reaches first quarter. The name refers to the moon completing 1/4 of its orbit around Earth, not the portion of its face we see lit. The moon now stands 90 degrees from the sun, perpendicular to the line connecting Earth and sun. This geometry means the moon rises around noon, reaches its highest point at sunset, and sets around midnight. First quarter. Moon is spectacular for lunar observation because the terminator, the line dividing day and night on the moon, runs straight down the center, and the low angle of sunlight creates dramatic shadows that emphasize the moon's topography, revealing crater depths and mountain heights. The moon continues to wax, entering the gibbous phase, from the Latin word for hump or bulge. The waxing gibbous moon shows more than half but less than complete illumination, growing fuller each night. The terminator continues its march across the lunar surface, revealing new features daily for observers with telescopes. The moon now rises in the afternoon and dominates the evening sky, setting after midnight. During this phase, the moon's brightness increases dramatically, not linearly but exponentially, because we're approaching the geometry where we see minimal shadows on the lunar surface. The full moon is over 10 times brighter than first quarter moon, not twice as bright, because at full phase we see no shadows at all, and light reflects most efficiently directly back toward its source. Then comes full moon, the moment when Earth lies directly between the sun and moon, and the entire face of the moon we can see is fully illuminated. The full moon rises at sunset, reaches its highest point at midnight, and sets at sunrise, exactly opposite the sun in the sky. The lunar surface appears flat and two-dimensional without shadows to reveal topography, but the overall effect is breathtakingly beautiful. The full moon provides enough light to read by, to cast shadows, to navigate by night. Ancient calendars worldwide used full moons to mark the passage of months, giving each full moon names reflecting seasonal activities: harvest moon, hunter's moon, snow moon. When the alignment is perfect and Earth's shadow falls on the moon, we witness a lunar eclipse, watching Earth's shadow creep across the lunar surface. After full moon, the cycle reverses. The waning gibbous moon, waning means shrinking, now shows the eastern limb beginning to darken as the terminator returns. The moon rises later each night, now after sunset, spending more time in the morning sky. Then comes third quarter, also called last quarter, again showing half illumination but with the opposite half lit compared to first quarter. The moon rises around midnight, reaches its highest point at sunrise, and sets around noon, perfect for early morning observation. Finally, the waning crescent appears as a delicate sliver in the eastern sky before dawn, thinning each morning until it disappears into the sun's glare, returning to new moon. The cycle takes 29.5 days, the synodic month, and has repeated billions of times since the moon formed. The phases you see depend on your location on Earth. In the northern hemisphere, the moon waxes from right to left. The waxing crescent appears on the right, growing leftward toward full moon. In the southern hemisphere, this reverses. Waxing occurs from left to right. Near the equator, crescents appear to smile or frown depending on the season, but the phases themselves are universal. Everyone on Earth sees the same phase simultaneously, just oriented differently in their sky. This monthly cycle has connected humanity across cultures and centuries, a shared celestial timepiece marking the rhythm of weeks and months. Next time you see the moon, take a moment to appreciate that you're witnessing not just reflected sunlight, but the beautiful geometry of three worlds in motion. Stand on a beach and watch the ocean for several hours, and you'll witness one of nature's most reliable rhythms, the rise and fall of the tides. Water advances up the shore, covering sand that was dry an hour before. Then it retreats, exposing rocks and tide pools. This rhythm occurs twice daily at most coastlines, with water rising and falling by amounts ranging from barely noticeable to over 16 meters taller than a 4-story building. For thousands of years, humans have recognized that tides connect somehow to the moon. But how can an object 384,400 kilometers away move billions of tons of water on Earth? The answer reveals one of gravity's most subtle and beautiful effects, one that shaped not just our oceans but the moon's orbit and Earth's rotation itself. Here's the key insight. The moon's gravity doesn't pull equally on all parts of Earth. It pulls hardest on the water directly facing the moon because that water is closest. It pulls less strongly on Earth's solid body at the center. And it pulls weakest on the water on the opposite side of Earth because that water is farthest away. This difference in gravitational force, called a tidal force, stretches Earth slightly, creating two bulges of water. One bulge forms on the side facing the moon, where the extra gravitational pull draws water toward the moon. The other bulge forms on the opposite side, where water is left behind as Earth itself is pulled more strongly toward the moon than that distant water. These two bulges remain roughly aligned with the moon as Earth rotates beneath them. As Earth rotates on its axis every 24 hours, any given point on Earth's surface passes through both tidal bulges, experiencing 2 high tides and 2 low tides each day. But there's a complication. The moon itself is orbiting Earth, moving eastward in the sky by about 13 degrees per day. This means Earth must rotate an extra 50 minutes beyond one complete rotation to catch up to the moon's new position. Consequently, the tidal cycle repeats every 24 hours and 50 minutes, causing high tides to occur about 50 minutes later each day. The sun also generates tides through the same mechanism, but despite the sun's enormous mass, its tidal effect is only about 46% as strong as the moon's, because tidal forces diminish with the cube of distance, and the sun is 390 times farther away. The combination of lunar and solar tides creates a twice-monthly rhythm of strong and weak tides. During new moon and full moon, when Earth, moon, and sun align in a straight line, their tidal forces add together constructively, creating spring tides, the highest high tides and lowest low tides of the month, producing the maximum tidal range. The name has nothing to do with the season. It comes from the tides springing forth. During first quarter and third quarter, moon, when the moon and sun form a right angle relative to Earth, their tidal forces partially cancel each other, creating neap tides, the smallest tidal range of the month, with lower high tides and higher low tides. This predictable cycle has governed ocean rhythms for billions of years. Tidal ranges vary dramatically around Earth due to local geography. In the open ocean, tides raise sea level by less than a meter, barely noticeable. But when tidal water flows into bays, channels, and gulfs, it can be amplified dramatically. The Bay of Fundy in Canada holds the record, with tidal ranges regularly reaching 16 meters over 50 feet during spring tides. Twice daily, 100 billion tons of water flow in and out of the bay. The enormous tidal range results from the bay's funnel shape concentrating water into a progressively narrower space, and resonance effects where the bay's natural oscillation period matches the tidal period, amplifying the effect. Tidal bores, walls of water that surge upstream in rivers during rising tides, can be surfed for kilometers in some locations. The moon's tidal influence extends beyond the oceans. Earth's solid body also experiences tides. The ground beneath your feet rises and falls by up to 30 centimeters twice daily as Earth deforms under the moon's gravitational force. You don't notice because everything around you moves together. The atmosphere experiences tides too, with air pressure variations of about 1 millibar. Even lakes can have small tides, though they're usually measured in centimeters rather than meters. The moon's gravitational reach touches every part of Earth, constantly kneading and flexing our planet. This ongoing deformation dissipates energy as friction, generating heat deep within Earth's interior. The tidal forces that move our oceans are simultaneously changing the length of our days and the moon's orbit in ways I'll reveal shortly. Ancient civilizations recognized tides but couldn't explain them. Aristotle noted the correlation with the moon but couldn't explain the mechanism. Medieval European scholars debated whether tides were caused by breathing of the earth or other mystical forces. Not until Isaac Newton published his law of universal gravitation in 1687 did humanity understand that tides result from the same force that keeps planets in orbit, gravity acting differently on different parts of a body? Newton's mathematics could predict tidal timing with remarkable accuracy. Today, we use his principles enhanced by centuries of observational data to predict tides years in advance, to within minutes. The tides that rise and fall on your local beach tonight were predicted decades ago with mathematical certainty, a testament to human understanding of celestial mechanics. Our journey now takes us deeper into one of the most profound gravitational relationships in the solar system. The ongoing exchange of energy between Earth and Moon that has shaped both worlds for billions of years. Right now, as you watch this, the Moon is slowly receding from Earth at 3.8 centimeters per year, the rate fingernails grow. Simultaneously, Earth's rotation is gradually slowing, making our days minutely longer with each passing century. These changes aren't random. They're the inevitable consequence of tidal forces operating over geological timespans. The Moon we see today orbits far from Earth compared to its birth position, and the 24-hour day we experience is much longer than the rapid spin of the young Earth. Understanding this dance reveals fundamental principles governing all orbital systems throughout the universe. Remember the tidal bulges the Moon creates in Earth's oceans? These bulges don't align perfectly with the Moon because of a crucial effect: friction. As Earth rotates beneath the tidal bulges, friction between moving water and the ocean floor and between ocean water and coastlines drags the bulges forward. Earth's rotation carries the tidal bulges approximately 50 minutes ahead of the Earth. Moonline. Now the Moon's gravity pulls on these misaligned bulges, and since they're ahead of the Moon, this gravitational pull acts as a drag on Earth's rotation, like a brake pedal slowing Earth's spin. Simultaneously, the bulges pull on the Moon gravitationally, accelerating it in its orbit. Conservation of angular momentum dictates that what Earth loses in rotational speed, the Moon gains in orbital motion. This energy transfer has been operating continuously for 4.5 billion years, gradually transforming both worlds. When the Moon formed and Earth completed one rotation in less than 10 hours, just a fraction of today's day length, the young Earth spun rapidly beneath an enormous nearby Moon. Tidal forces were tremendously stronger then, and the slowing happened relatively quickly at first. About 4.5 billion years ago, the day was under 10 hours long. By 2.5 billion years ago, it had increased to about 17 hours. By 600 million years ago, when complex life was beginning to flourish, a day lasted approximately 21.9 hours, and the year contained 400 days. During the age of dinosaurs 245 million years ago, days were 22.5 hours long. Each century, our day grows longer by 1.7 to 2.4 milliseconds, an imperceptible change to humans but geologically significant over millions of years. Remarkably, Earth's day stabilized for over 1.5 billion years during what scientists call the boring billion, between 2 billion and 600 million years ago. Despite tidal forces continuing to operate, day length remained locked at approximately 19.5 hours for this entire epoch. Guide. Why? The atmosphere itself provided a counterbalancing force. Atmospheric thermal tides driven by solar heating happened to have a natural resonance period that matched the day length during this period. These atmospheric tides pushed against the ocean tides, creating a perfect balance that prevented further lengthening of the day. Only when Earth's day length exceeded this resonance period did the slowing resume. Without this billion-year pause, today's day would stretch beyond 60 hours, profoundly altering Earth's climate and biology. As Earth's rotation slows, the Moon must move farther away to conserve angular momentum. The recession rate varies with the strength of tidal forces and Earth's oceanic configuration. Currently, the moon recedes at 3.8 centimeters per year, an unusually high rate because of resonances in the North Atlantic Ocean, where 41% of global tidal energy dissipates in a relatively small basin. Over geological history, the recession rate has varied from about 2 centimeters per year, averaged over the past 2.5 billion years. Lunar laser. Ranging experiments, which bounce laser beams off retroreflectors left by Apollo astronauts and measure the round-trip time to centimeter precision, confirm the current recession rate directly. The moon that illuminated Earth. 100 million years ago was about 3,800 kilometers closer than today. This recession has profound, long-term consequences. In about 600 million years, the moon will appear too small in the sky to completely cover the sun's disk during eclipses. Total solar eclipses, among nature's most spectacular phenomena, will no longer be possible from Earth's surface. Only annular eclipses, where a ring of sunlight remains visible around the moon's silhouette, will occur. We live in a cosmically privileged epoch when the moon and sun appear almost exactly the same size in our sky, a coincidence that has allowed total solar eclipses and enabled early scientists to study the sun's corona and confirm Einstein's general relativity. Future civilizations, if any exist on Earth, 600 million years hence, will never experience the awe of totality when day turns to night and stars appear at noon. The tidal interaction between Earth and Moon will continue far into the future, assuming both worlds survive the Sun's red giant phase in 5 billion years. Eventually, in approximately 50 billion years, the Earth-Moon system would reach a final equilibrium state with both bodies tidally locked to each other. Earth's rotation period would equal the Moon's orbital period, both lasting about 47 current Earth days. From one hemisphere of Earth, the Moon would hang stationary in the sky, never rising or setting, appearing about 40% larger than today due to a closer final orbital distance. From the other hemisphere, the Moon would never be visible at all. At this point, tidal forces would cease to transfer energy, the perfect synchronization eliminating further change. But the sun will become a red giant long before this happens, likely engulfing both worlds. We shall go down together. We've explored the moon's surface, its phases, and its gravitational effects on Earth's oceans and rotation. Now we must ask a more profound question. Could complex life exist on Earth without the moon? The answer isn't simple, but evidence increasingly suggests that our oversized moon, the largest relative to its planet in the inner solar system, may have been essential for life's development. The moon's influence extends beyond romantic inspiration and navigational aid. It fundamentally shaped Earth's environment, creating conditions stable enough for life to evolve from simple cells to complex multicellular organisms, and eventually to conscious beings capable of looking back at their ancient companion and understanding the connection. Let's explore how a cosmic collision 4.5 billion years ago may have inadvertently created the conditions for your existence. The moon's most crucial contribution to Earth's habitability is axial stabilization. Earth's axis currently tilts 23.5 degrees from perpendicular to its orbital plane around the Sun. This tilt gives us our seasons, as hemispheres tilt toward or away from the Sun during the year. Without the moon, this tilt would be unstable, varying chaotically by at least 10 degrees and possibly ranging from 0 to 85 degrees over periods of just millions of years. A landmark 1993 study showed that without lunar stabilization, Earth's obliquity could reach extreme values, causing the Sun to swing from directly over the equator to directly over the poles. Such dramatic variations would create climate chaos. Regions would experience centuries of perpetual summer followed by endless winter. Ice ages would alternate with scorching heat with frightening rapidity. How does the moon stabilize Earth's axis? through angular momentum. The moon adds angular momentum to the Earth. Moon system comparable to Earth's rotational angular momentum. The moon's gravitational tug on Earth's equatorial bulge creates a torque that speeds up the precession of Earth's axis, the slow wobbling motion like a spinning top. This enhanced precession acts like a gyroscope, resisting dramatic changes in tilt from gravitational perturbations from the Sun and Jupiter. Mars provides a sobering comparison. Its two tiny moons, Phobos and Deimos, provide negligible stabilization, and Mars's axial tilt has varied between 10 and 60 degrees over millions of years. These wild swings contributed to the loss of Mars's atmosphere and transformation from a potentially habitable world to the cold desert we see today. Earth avoided this fate because of its large moon. Beyond axial stabilization, the moon's tides may have provided the physical conditions where life originated. Molecular biologist Richard Lathe proposes that 3.9 billion years ago, when Earth's day was just 12 hours and high tides occurred every 6 hours, the rapid tidal cycling created perfect conditions for the formation of precursor molecules that eventually became DNA and RNA. Picture vast, flat coastal regions where tides moved kilometers inland every few hours. At low tide, water trapped in shallow pools evaporated in the hot sun, concentrating organic molecules and dissolved salts. This saline environment allowed protonucleic acid fragments to associate and assemble complementary strands, a crude form of molecular replication. At high tide, fresher water flowed in, reducing salinity and causing the newly formed molecules to separate. This repeated cycle of concentration and dilution may have been the engine that started life's molecular machinery. Tidal zones continue to drive evolution throughout Earth's history. The intertidal zone, the region between high and low tide marks, experiences extreme environmental pressures over short distances. Species must adapt to being submerged underwater for hours, then exposed to air, sun, and temperature extremes. This zone forced remarkable innovations. Limpets evolved, teeth that are the strongest biological material ever tested, 5 times stronger than spider silk. Rocky intertidal areas provided the transitional environment where aquatic life first ventured onto land. Fish trapped in tidal pools developed weight-bearing limbs and air-breathing organs. The lineages that ultimately gave rise to humans were at first intertidal. Without the moon's tides creating these dynamic shoreline environments, the evolution of terrestrial life might have been delayed indefinitely or taken radically different paths. The moon's tides continuously shape Earth's oceans in ways that support life. Tidal currents mix warm and cold water, distributing heat from the equator toward the poles and moderating climate extremes. The rise and fall of tides brings nutrient-rich water from the ocean floor to the surface, supporting the base of marine food chains. In estuaries, river mouths, and coastal bays, tidal flow creates incredibly productive ecosystems. Mangrove forests, salt marshes, and coral reefs that host immense biodiversity and serve as nurseries for countless species. Tidal energy drives oceanic circulation patterns that influence global climate. The approximately 3.7 terawatts of energy dissipated by tides, equivalent to millions of homes' electricity consumption, helps transport heat around the planet. Without tidal mixing, our oceans would be stratified, stagnant, and far less hospitable to life. The moon has also given humanity the gift of predictable time beyond the daily cycle of sunrise and sunset. The synodic month. Nearly every culture developed lunar calendars to track seasons for agriculture, religious observances, and navigation. The word month derives from moon. Even today, many cultural and religious calendars remain lunar-based. The moon's phases are visible to everyone simultaneously, creating a shared temporal reference across the entire planet, a synchronizing clock that helped early human societies coordinate activities and develop agriculture. The reliable cycling of lunar phases, combined with the sun's annual path, allowed ancient astronomers to predict eclipses, understand the heavens, and ultimately develop the scientific method that has revealed the universe to us. Imagine Earth without the moon. The sky would be darker, lacking the brilliant full moon that has inspired countless poets, lovers, and artists. Tides would still exist from the sun alone, but they'd be only 46% as strong, gentle risings rather than dramatic floods. The day would possibly be much longer, perhaps 60+ hours, with extreme temperature swings between extended days and nights. Most critically, Earth's axis would wobble chaotically, creating climate instability that might have prevented complex life from ever developing. We would live on a fundamentally different planet if we could live there at all. The moon isn't just our satellite. It's our silent guardian, the cosmic architect that sculpted conditions making Earth not just habitable, but welcoming to the rich biosphere we cherish. We exist in part because a Mars-sized world struck Earth 4.5 billion years ago. For decades after the Apollo program ended in 1972, the moon seemed like a finished chapter in exploration, a world fully understood, catalogued, and set aside while humanity turned its attention elsewhere. But the past decade has shattered this complacency. Lunar science is experiencing a renaissance. Missions from China, India, Japan, and commercial companies have returned to the moon, and their discoveries have fundamentally revised our understanding of our ancient companion. The supposedly dead, dry, geologically inactive moon has revealed itself to be far more dynamic, mysterious, and resource-rich than anyone imagined. Water ice deposits exist at the poles. Volcanic activity continued until dinosaurs walked Earth. Far-side samples reveal profound mysteries about lunar asymmetry. Join me as we explore the discoveries rewriting lunar science. In December 2020, China's Chang'e 5 mission returned 1,731 grams of samples from Oceanus Procellarum, ending a 44-year drought in lunar sample returns. Scientists expected ancient basalts like Apollo samples. Instead, radiometric dating revealed basalts that crystallized just 2.03 billion years ago, extending known volcanism by 800 to 900 million years. The moon remained volcanically active until at least 2 billion years ago, far beyond when thermal models predicted volcanism should have ceased. Even more astonishing, volcanic glass beads dated to just 123 million years ago prove magma reached the surface while dinosaurs roamed Earth. During Earth's Cretaceous period, the supposedly dead moon was alive far more recently than anyone dreamed. This discovery forces us to reconsider the thermal evolution of all rocky worlds. In June 2024, China achieved another historic first. Chang'e 6 returned 1,935 grams of samples from the lunar far side, the first material ever retrieved from the hemisphere permanently facing away from Earth. The landing site in the South Pole, Aitken Basin. Analysis revealed basalts dated to 2 to 807 billion years ago with distinctly different chemistry from near-side samples, lower in KREV elements and showing different mineralogy. These samples confirm the profound asymmetry between the two hemispheres, but they also deepen the mystery. Why did the moon develop two such different faces? Understanding this asymmetry may reveal fundamental truths about how the moon formed and differentiated, potentially revolutionizing planetary science for worlds throughout the universe. Water on the moon. The idea seemed absurd during the Apollo era. Astronauts described the moon as bone dry, and laboratory analysis of Apollo samples initially found no water whatsoever. For decades, the moon was considered completely desiccated, lacking even traces of water molecules. Then, beginning in 2009, everything changed. India's Chandrayaan. 1. Mission detected water molecules on the sunlit surface. NASA's L-Cross mission intentionally crashed into a permanently shadowed crater and detected significant water ice in the ejected plume. The Lunar Reconnaissance Orbiter's instruments mapped widespread water signatures. In October 2024, comprehensive analysis revealed water ice deposits covering over 1,660 square kilometers at both poles, twice what we previously knew about, with concentrations reaching 5 liters per square meter in some permanently shadowed regions. The supposedly dry moon holds enough water to support human exploration. Commercial spaceflight has finally arrived at the moon. In February 2024, Intuitive Machines' Odysseus lander became the first private spacecraft to soft land on the moon, touching down near the South Pole, also the first U.S. lunar landing since Apollo 17 in 1972. Though the lander tipped over due to a navigation issue, it transmitted data for a week, proving commercial lunar access is achievable. Japan's SLIM demonstrated precision landing within 100 meters of its target technology, crucial for landing at specific high-value scientific sites. Firefly's Blue Ghost landed successfully in March 2025 without tipping. Multiple companies are now competing to deliver payloads to the moon at a fraction of government program costs. This commercial revolution means sustained lunar presence is no longer limited to superpowers, but accessible to universities, companies, and even individuals with the resources and vision. NASA's Lunar Reconnaissance Orbiter has been silently revolutionizing lunar science since 2009, orbiting just 50 kilometers above the surface. Its high-resolution cameras have mapped the entire moon at unprecedented detail, revealing everything from new craters forming in real time to the precise locations of all Apollo landing sites. You can even see the rovers and experiments the astronauts left behind, casting shadows in the lunar sunlight. The Diviner instrument measured temperatures in permanently shadowed craters reaching 248 degrees C, among the coldest places in the solar system. Laser altimeter data created topographic maps accurate to meters. Lola's measurements revealed that the moon's shape is actually slightly egg-shaped, bulging toward and away from Earth. After 15 years, LRO continues making discoveries, proving that persistent observation reveals secrets even of worlds we thought we knew well. International cooperation and competition are driving a new lunar race. India's Chandrayaan-3 successfully landed at the South Pole in August 2023, making India the fourth nation to soft land on the moon and first to reach the polar region. The Pragyan rover explored the ancient terrain for 2 weeks during the lunar day. India plans Chandrayaan. 4. Sample return from the South Pole in 2028, aiming to collect 3 kilograms of material from this scientifically rich region. Japan has joined forces with India on the LUPEX mission, deploying a 350-kilogram rover capable of drilling 1.5 meters deep to sample subsurface ice. Russia plans Luna 26 orbiter in 2027 and Luna 27 polar lander with drilling capability. The moon is once again the focus of international prestige and scientific ambition, just as it was in the 1960s. But this time, many more players compete and cooperate. Perhaps the most intriguing recent discovery is how much we still don't know. The moon's far side remains profoundly mysterious despite Chang'e samples. Why is it so different from the near side? What caused the asymmetry in crustal thickness and volcanic activity? Grail gravity data revealed massive mass concentrations beneath impact basins, but their precise nature remains debated. The moon may have a partially molten layer at the base of its mantle, but its extent and composition need confirmation. Mysterious transient lunar phenomena. Flashes of light observed by astronomers for centuries lack satisfactory explanation. Swirls of high albedo material with associated magnetic anomalies suggest the moon once had a magnetic field, but when and why it disappeared remains unclear. Every answer reveals new questions, and that's what makes lunar science so compelling right now. We're rediscovering our oldest companion. The year 2027 will mark humanity's return to the moon after a 55-year absence, the longest gap since we first reached another world. But this time, we're not planting flags and footprints only to leave and never return. This time, we're building the infrastructure for permanent human presence beyond Earth. NASA's Artemis program, working with international and commercial partners, will establish the foundations of a lunar economy, habitats, rovers, power systems, communication networks, and resource extraction facilities. The first Artemis 3 astronauts will walk on lunar soil, not as visitors but as pioneers preparing the way for those who will follow. After 5 decades of robotic missions and orbital observations, humans will once again stand on another world, looking up at Earth hanging in the black sky. And this time, we will stay. Artemis II, launching in February 2026, will send 4 astronauts around the moon. Americans, Reed Wiseman, Victor Glover, Christina Koch, and Canadian Jeremy Hansen. Named Integrity by their crew, the Orion spacecraft will complete a 10-day mission flying within 6,000 miles of the lunar surface, testing all systems needed for landing missions. The crew will become the first humans to see the far side with their own eyes since Apollo 17 in 1972, witnessing the dramatic difference between the heavily cratered far side and Maria-covered near side. They'll conduct observations of potential landing sites, test communication systems, and validate the Orion heat shield after improvements following Artemis I's teens. This mission represents the final stepping stone before humans walk on the moon again, a test of everything except the landing itself. Artemis 3 in mid-2027 will be the historic moment, the first human lunar landing since Apollo 17, the first woman on the moon, the first person of color on the moon. 2 astronauts will spend approximately 7 days on the surface near the South Pole, conducting 4 spacewalks to collect samples, deploy scientific instruments, and search for water ice in permanently shadowed regions. They'll use SpaceX's Starship Human Landing System, a 50-meter tall vehicle capable of carrying large payloads and providing spacious living quarters compared to the cramped Apollo lunar module. The landing site will be in one of 9 candidate regions near the South Pole, all within reach of both ancient highland rocks over 385 billion years old and water ice deposits. This mission doesn't just resume exploration, it establishes beachheads for permanent presence. Gateway, humanity's first space station beyond Earth orbit, will serve as the staging post for lunar missions, beginning with the launch of its first 2 modules in 2027, the power and propulsion element, and the habitation and logistics outpost. Gateway will be assembled in a near rectilinear halo orbit ranging from 7,000 to 70,000 kilometers from the Moon. This unique orbit requires minimal fuel to maintain and provides continuous Earth communication while giving access to the entire lunar surface. Up to 4 astronauts will live aboard Gateway for approximately 90 days at a time, conducting scientific research, controlling surface robots, and preparing for landing missions. International modules from Europe, Japan, and the UAE will expand Gateway's capabilities. Life support, robotics, airlocks, and refueling systems, creating a truly global outpost in deep space. Beyond the initial landings, Artemis will build genuine infrastructure. By Artemis VII in 2032, the foundation habitat and mobile habitat will arrive, permanent structures where astronauts can live for months, not days. JAXA and Toyota are developing the Lunar Cruiser, a pressurized rover capable of carrying 2 to 4 astronauts over 10,000-kilometer ranges, equivalent to driving from New York to Los Angeles and back. Imagine exploring the moon, not in walking distance day trips, but in week-long expeditions covering hundreds of kilometers, reaching diverse geological features, sampling different terrains, and discovering resources across vast regions. Power systems, communication networks, landing pads, and resource extraction facilities will transform patches of lunar surface into functioning bases where humans can live and work sustainably. In UZ, resource utilization. Using local materials rather than bringing everything from Earth transforms from concept to reality. Water ice in permanently shadowed craters will be extracted through drilling and thermal heating, then split into hydrogen and oxygen. Oxygen becomes breathable air and rocket oxidizer. Hydrogen provides rocket fuel and energy storage. Just extracting and processing 1,000 kilograms of water per year, a modest initial goal, could support a small crew and refuel multiple lunar ascent vehicles, dramatically reducing mission costs. Oxygen extraction from Regolith could produce thousands of kilograms annually, since oxygen comprises 45% of lunar soil by weight. China's Chang'e mission in 2028 will demonstrate 3D printing lunar bricks, proving we can build structures from local materials. These technologies turn the moon from a destination requiring constant Earth resupply into a world that provides for its inhabitants. International programs create parallel pathways to sustained lunar presence. China targets landing astronauts by 2030 and establishing the International Lunar Research Station, co-led with Russia, during the 2030s, with 17 countries already partnered. India aims for crewed landing by 2040 and a lunar base before 2050. Japan contributes critical technology, including the Lunar Cruiser rover and Gateway modules, with agreements securing Japanese astronaut seats on future surface missions, the first non-Americans who will walk on the moon. The European Space Agency provides multiple Gateway modules and is developing robotic sample return capabilities. Rather than a single national program, lunar exploration has become a truly international endeavor, with cooperation and competition driving rapid progress. By 2035, multiple bases operated by different nations may exist on the lunar surface simultaneously, a permanent human presence among the stars. The vision extends beyond the moon itself. Lunar bases will serve as testbeds for technologies needed for Mars missions. Closed-loop life support, radiation protection, long-duration habitation, and resource utilization. The moon becomes a training ground where we learn to live sustainably on other worlds before attempting the vastly more difficult Mars journey. Gateway will evolve into a transportation hub, not just for lunar missions, but for spacecraft heading deeper into the solar system. Mining operations might extract rare earth elements or helium-3, creating economic incentives beyond science and exploration. Perhaps most importantly, permanent lunar presence fundamentally changes humanity's perspective. We become a multi-world species, our survival no longer dependent on a single fragile planet. The moon represents not an endpoint, but a beginning. the first step toward a future among the stars. We've journeyed together across 4.5 billion years, from a catastrophic collision that created two worlds from one, through the moon's slow cooling and differentiation across its scarred and cratered surface, through the monthly cycle of phases that has marked human time since our species emerged. We've explored how the moon moves our oceans, slows our planet's rotation, and may have made complex life possible through its stabilizing influence. We've witnessed recent discoveries that shattered old assumptions and revealed new mysteries. And we've glimpsed the future where humans return, not as visitors, but as permanent residents, building the infrastructure for sustained presence among the stars. Now, as our journey concludes, let's reflect on what the moon means to us, not just scientifically, but existentially. Throughout human history, every culture has looked up at the moon and seen meaning. Ancient Sumerians tracked lunar cycles 5,000 years ago, creating the first calendars. Chinese poets wrote of the moon's beauty and melancholy for millennia. Islamic scholars used lunar observations to refine mathematics and astronomy. Indigenous peoples worldwide incorporated the moon into creation myths and seasonal calendars. The moon has been goddess and god, symbol of femininity and fertility, marker of time and navigation guide. Before we understood its true nature as a world formed by cosmic violence, before we knew it was made of the same rock and metal as Earth, before we walked on its surface, the moon was already deeply woven into human culture and consciousness. Our relationship with the moon spans not just the space age, but the entirety of human existence. When Apollo 8 orbited the moon on Christmas Eve 1968, astronaut William Anders photographed Earth rising over the lunar horizon, a blue and white marble floating in the black void, clouds swirling over oceans and continents. This single image, called Earthrise, fundamentally changed human consciousness. For the first time, we saw our world from beyond, saw its fragility and beauty, saw that it was a finite sphere isolated in an infinite cosmos. The environmental movement gained momentum. People began thinking globally about our shared home. The overview effect, the cognitive shift in awareness reported by astronauts seeing Earth from space, became part of human culture. The moon, by giving us a vantage point from which to see ourselves, taught us about Earth. The moon also reminds us of our capability. When President Kennedy challenged the nation to reach the moon before the decade ended, many considered it impossible. Yet through determination, ingenuity, and the coordinated effort of over 400,000 people, humanity achieved what seemed unachievable. The Apollo program represented not just technological achievement, but the power of human cooperation toward a common goal. The moon became proof that we could accomplish extraordinary things when we chose to focus our collective abilities. Today, as we face challenges that require similar cooperation, climate change, resource sustainability, pandemic response, the moon reminds us of our potential. The moon is also deeply personal. How many people have shared their first kiss under moonlight? How many poems have been written to the moon? How many children have asked their parents why the moon follows them as they drive down dark roads? The moon appears in our songs, our literature, our dreams. It marks our month and influences our language. Lunatic, month, Monday, crescent. It creates the spectacle of eclipses that draws millions outdoors to witness celestial alignment. During power outages, it provides emergency light. On dark nights far from cities, the full moon illuminates the landscape enough to walk without artificial light. The moon isn't just a scientific object or resource to be exploited. It's part of human experience in ways profound and trivial, practical and romantic. Looking forward, the moon will become something new, a place where humans live and work, a resource to be utilized, a stepping stone to Mars and beyond. This transformation from distant celestial object to accessible world will change our relationship with it once again. Children born in lunar bases will experience 1 sign 6 Earth's gravity as normal. They'll watch Earth rise and set from permanent habitats. The moon will transition from symbol and inspiration to home for some, workplace for others, destination for tourists eventually. This domestication of the moon might diminish some of its mystery and romance, but it also fulfills ancient dreams of human expansion beyond our birth world. We don't lose the moon by understanding and inhabiting it. We deepen our relationship with it, adding lived experience to observation and imagination. Here's what strikes me most. The moon and Earth are locked in a gravitational embrace that has lasted 4.5 billion years and will continue until the sun destroys both worlds. They formed together from violence, cooled together through eons, influenced each other's evolution in countless ways. Earth gave the moon material during the giant impact. The moon gave Earth stable climate through axial stabilization. Earth's tides slowly push the moon away, while the moon's gravity slows Earth's rotation. They're partners in an orbital dance that will continue far beyond humanity's existence. Whatever we do on the moon, building bases, extracting resources, conducting science, occurs in the context of this ancient partnership between two worlds. We're not conquerors, but temporary participants in a relationship billions of years old. So the next time you see the moon, remember that you're seeing an entire world with mountains taller than Everest, canyons deeper than the Grand Canyon, plains the size of seas. Remember, it formed 4.51 billion years ago in an impact that would have ended life had life existed then. Remember, it has shaped Earth's environment, making complex life possible. Remember that 12 humans have walked there, and soon others will return. Remember that it moves our oceans, slows our rotation, lights our nights. Remember that humans across all cultures and times have looked at the same moon and felt connection, wonder, and curiosity. Or constant companion, our ancient dance partner, our gateway to the stars. The moon. Thank you for joining me on this journey across time and space to explore our closest cosmic companion. The moon has been humanity's constant friend for all of our existence, and it will continue to light our nights and inspire our dreams far into the future. As we return to the moon in the coming years, remember that you're witnessing history, the transformation from exploration to habitation, from visiting to staying, from one world to many. If this journey brought you peace, wonder, or new understanding, consider subscribing to Cosmic Calm for more serene explorations of the universe. Until we meet again under the light of the moon, may you find tranquility in the vast cosmos that surrounds us all.